Okay, so on the data structures, the one for mail I'd gone over a number of times in class said that the key things here was that the email needs to be ordered in ascending order by date, which means you're going to have to use some kind of data structure which orders that information, which means map set, multi-map, or multi-set. And then it said the email needs to store a key, which is the date, and a value. So that eliminates the set. So now we're down to a map and a multi-map. And it said the dates might not be unique, which eliminated the map, because if the dates are not unique, then you have to store potentially multiple dates with the same value, and that means you have to use a multi-map for that. On H, I know that most of you had set itis probably on your minds from the lab, and I did give you partial credit if you chose a set for this one, but in fact, if you think about it, a hash table is in fact the best strategy for determining whether a phone number is already in use, because the last sentence said the phone numbers do not need to be ordered. So you typically use maps and sets when your data has to be ordered. If all you're concerned about is fast inserts, retrievals, and deletes, you should use a hash table, because that's order one time or constant time access in general, whereas a set or a map is order login time. So again, I gave you partial credit, and if you didn't get partial credit, I'll be happy to give you some if you chose a set here. Yes?
What about a list?
Pardon?
A list?
A list is not a very good choice because it's going to take order n time. You may have to do a complete linear search of the list in order to determine whether a phone number is in use. Because if that phone number is at the end of the list, then you have to search the entire list, and that's order n time, which is can be quite slow. Okay. Other questions? Okay, on the next one, the data structure which allows any of its elements to be accessed in guaranteed constant time. The only thing that can actually, well, based on what I've told you, is a vector. I think some of you put down hash table, but a hash table is not guaranteed to be constant time. In the worst case, if all the keys hash to the same value, which is admittedly not likely but can happen, then it's order n time. So it's not guaranteed constant time for a hash table, where it is always guaranteed constant time for a vector. Okay. Data structure you would use if you needed to be able to delete an element in the middle of an unordered data structure. It's unordered, okay, and from the middle, that means a list. Okay, data structure you should use if you want to print out the last n lines of a file where n is a command line argument. You should only hold n lines of the file in memory at any time. So I gave partial credit on this one. I believe if you used a list, Alan, do you remember what else was partial credit? I know a list was one. But in class, I'd emphasize that if you are adding or deleting from the beginning or end of a data structure, you should use a DQ. And so that was the answer that I was looking for here, because if you're only holding n lines of the file in memory at any time, you're always adding a line to the end, and you're potentially removing a line from the beginning, and that's the perfect data structure, or the DQ is a perfect data structure there. This was, yeah, 1, 2, 3, 4, 5.
1 point per vector. Wait, but this says full credit was list. I'm confused.
Uh-oh. 1, 2, 3, 4, 5. Let's see. Maybe we have a, let's see what the grading guide said. 5, 2 points, wow. Okay, you may have, okay, so it looks like the grading guide's differing from the exam, so you definitely need to take a hard look at your exam here. If you got, oh no, that's not true. It was worth, yeah, 3 points. I gave 2 points partial credit if they chose a list. 1 point partial credit for a vector.
Oh, so they got full credit.
Right, they got 3 points for a DQ, 2 points for a list, 1 point for a vector. So you got 1 point off for choosing a list, 2 points off for choosing a vector. Okay, so those were the other 2 data structures you could have used, but didn't consider them to be quite as good. Now for C, this was really hitting you over the head with a DQ because it's saying we want to simulate an unbounded line of customers. Customers are served from the front of the line. Customers enter at the back of the line. Just kind of a classic case for a Q, in this case a DQ. Okay, Mark.
I guess on this, why can't you use the list since they both, a DQ, double with the Q.
Right, it's just, right, because the DQ is going to be more efficient and use less storage typically. A DQ can be implemented efficiently as a vector and it's going to use less storage. And also because you don't have to follow pointers, it's going to be a more efficient access. You can. It's just the list is not quite as efficient. Okay? Because a DQ is implemented, vectors are more efficient than lists. Okay? So the answer is yes. You could simulate it using a list. It's just not as efficient. Okay? Not sure if I gave... Yeah, so here again, you got 2 points if you chose list. So you still got most of the points. It's just not as efficient. The big thing about this course is data structures and choosing the right data structure for the task and knowing which are the most efficient and the like. So, okay. Finally, the last one, data structure should store race results keyed on finish times. I said that the finish times are unique and the runners should be stored in sorted order. All of that is pointing to either a map or a set. And it says there's keyed on a finish time and store a value, which is the name of the runner. Therefore, you have to use a map because it's a key value pair. Okay, so any other questions about that? Okay, question 4. A lot of you answered A and B correctly, but then for X and Y, you answered as though I had put a dereferencing operator in front of them, which is not, for some reason, picking up right now. Huh. Okay, so I can't, there we go. It's delayed. Okay, so many of you answered as though I had put the dereferencing operator in front of the X and the Y, but I didn't. Okay, if you look at Dr. Planck's exam, which I suspect many of you too closely were following, when he printed out those values, he put dereferencing operators in front of the pointers. But that wasn't done here. We were just asking literally for the values of X and Y, and X and Y store addresses because they're pointer variables. They do not store values. So in fact, X and Y, X stored the address of B, B is 0x1004, so that was the contents of X, and Y was set equal to X, therefore Y also was 0x1004. Okay, so you need to be, it's important that you distinguish between the value of a pointer, which is an address, and the dereferenced value of a pointer, which is the value of memory to which it points, or the value of the memory at that address. Okay? Okay, for question 6, I got a lot of answers that said dangling pointer rather than memory leak. So there is an important difference between a dangling pointer and a memory leak. In fact, so a dangling pointer is a pointer to a deleted block of memory. Okay, so you've deleted a block of memory, but some other pointer still points to it. So that would have been a situation if I had had, in addition to int x, if I had then said x equals new int, y equals x, delete x, that would have now, y would have been a dangling pointer because x and y both point to the same block of memory. I deleted x and y still points to it. So y would be a dangling pointer. But that's not the situation that exists here. The situation that exists here is that I allocated with this statement a piece of memory, an integer. With this statement, I assigned that piece of memory the value 40. With this statement, I assigned a new block of memory and made x point to it. That means that x no longer pointed to 40. And not only did x no longer point to 40, there's no other pointer pointing to 40 either. Which means I have a memory leak because that piece of memory containing 40 is never going to get deleted. It's never going to be returned to the memory manager. So that's a memory leak when a piece of memory does not get returned to the memory manager once there are no more pointers to it. So is that distinction between a dangling pointer and a memory leak clear? You're going to hear this term a lot in your CS career, these two terms. And they're two very different concepts. You need to be familiar with them. Forrest, you look like, no? You're good. Sarah?
Can you remind me real quick what, so I understand what a memory leak is, but I'm not completely sure how a pointer.
What a dangling pointer is?
Yeah.
Okay, so we'll go back over a dangling pointer again. So this code right here, if I'd given you this code, that code would lead to a dangling pointer situation.
Right.
Because I would have started out and x would have pointed to that piece of memory. Then I would have set y to point to that piece of memory with this statement right here. Then this statement would delete x, okay, and it causes a dangling pointer situation. We tend to know that x is right now a dangling pointer. We actually don't think of x as a dangling pointer, but we do think of y as a dangling pointer because most likely we had forgotten that y still pointed to that piece of memory. Okay. Other questions about it? Gerald.
Is there something called a lost object?
Yeah, that's
A lost object is the same as a memory leak. So if you hear the word lost object,
I got points taken.
because that's not real. Okay, I'll give you some points back if you show it to me. Okay, the term we want, the term that you will hear used is memory leak. So, but I will give you points back. So, Senia, also if you said lost object, I'll give you points back.
Is lost out there two different things?
No, they refer to the same.
But you just wanted to.
We want you to use the term memory leak. Memory leak is used like if you were in professional circles, people are going to talk about memory leaks rather than lost objects. So it's just one of those things. I want you to get familiar with our jargon because
I think it's how it's set on the problems. It's
Yeah.
lost
On the
objects,
what?
problems.
All the problems that we did. Like
Ah,
that are
excellent.
all lost
Okay.
objects.
gotcha. Well, as I said, if you show it to me, I will give you 4 points back. Okay, because certainly you have the right idea. So anyone who said lost object, I'll give 4 points to.
I got 3 points.
Yeah.
Okay, I'll give you a 4th. I'm not going to give you the full thing, but I'll give you 1 more point if you want it. I don't think it'll make a difference in any of your 3 grades, but okay. Other questions? Okay. So, question 6. Explain what is wrong with the following code segment. It says use no more than 3 sentences to describe the problem. So, what this code segment was trying to do was keep track for each person, their set of friends. So, essentially, what I had was I conceptually had a map with names, like say BVZ, Mary, Smiley, and conceptually each of them pointed to a set which had their friends. Okay, so this is a conceptual representation of it. They're not actually stored as vectors, they're stored as maps and sets, but conceptually this is what we had. And what this piece of code right here was supposed to do was read a friend relationship and add friend 2 to friend 1's set. So friend 1 claimed that friend 2 was a friend. We wanted to add friend 2 to friend 1. So for example, if I read in BVZ Mary, the idea is that Mary would get added to BVZ's friend set. And I understand, I saw a couple answers that said, well, if the friend doesn't exist, the code will fail. And I gave some partial credit. Alan, I'm not sure what happened on your, do you know on question 6 whether partial credit was given for an answer that said, if the friend doesn't exist, there's no check for it?
No, I didn't give I don't think I gave any partial credit for that.
Okay. It was a issue, and if I will say that if you said that I didn't give Alan guidance on this, it's only after the fact. I was grading some makeups. I decided to give 3 points if you said that the code should have checked to see if a friend was in the map. That is true, but that's not the real issue with this code. The real issue with this code is that when you find the friend, like BVZ, this statement right here is a doozy. What it does is it actually creates a copy of this set right here, and it assigns it to friend set. So it creates a completely new and different copy of that set that's completely different from this set right here. That's the warning that Dr. Planck was giving you in his notes on maps and sets. If you go back to his notes on sets and maps. Is that it? Yes, it said you should use pointers as the val part of a map. And he gave the example in this section of what happens if you forget to do so. And it's such an important concept that I wanted to test you over it because it leads to bad bugs in the program. In this case, the bug is that friend set now points to this completely new chunk of memory and you add Mary to it. And with this statement right here, you add Mary to it, but it's not adding it to the right set. This is the set that you want it to add Mary to, not this set, which is actually going to completely disappear at the end of the function. So that is why Dr. Planck made such a big deal of the fact that you need to use pointers in this situation, and that will force you to say things like friends IT second, say dot insert. Actually, let's see. Nope. Friends insert arrow, insert friend 2. So the fact that you're using pointers kind of forces you into using the correct syntax. And if you don't, the compiler is going to complain. Okay, so this is a really important point because if you fall into this trap of not using pointers to objects that are values in your maps, then you may easily find buggy code because you may try to do this kind of thing where you set a temporary variable to the object and you end up with a copy rather than the object you're trying to modify. So is that clear? Okay, this will come back to haunt you in your own code if you aren't careful with this particular type of bug. Okay. Question 7 seemed many of you got. There was a couple things that I saw. There was some missing of the Sentinel nodes. So lists have Sentinel nodes. Dr. Planck showed 2. If you only showed 1, that was fine because in fact that's how I believe STL lists are implemented, is with only 1 Sentinel node. But since he showed 2, that's how I chose to show my solution. If you look, I saw some things where people just wrote down Joe, Mary, Nancy, Tom, but you'll notice that the first 2 were pushbacks and the second 2 were push fronts. So I was testing whether you had the right, if you kind of knew the difference between them. So the first pushback puts Joe on the list. The pushback adds Mary to the back of the list. Then the push front here adds Tom to the front of the list. And the final push front adds Nancy. And the final push front adds Tom, which is why I get the data structure you see there. And they're doubly linked, the lists. Then the 3 iterators, when names.begin right here, returns a pointer to the first list element. And then when I say knit++ right here, that increments knit so that it points to Nancy. So that's the first one. Then when you use rbegin, that sets rnit to be a pointer to the last list element. And finally, I wanted to see if you knew what happened with names.end. That actually returns a pointer to the sentinel node. Many of you showed it as being a pointer to the last element in the list, which is incorrect. In fact, the end method returns a pointer to the sentinel node. That's how you know that you've reached the end of the list, is when you reach the sentinel node. Okay, if end actually pointed to the last element of the list and you wrote something like for nit equals, sorry, this was nit1. So nit1 equals names.begin. And you said nit1 not equal names.end. If names.end returned a pointer to the last item of the list, which was Mary, then it would, the first time through the loop, nit1 would point to Tom. The second time it would point to Nancy. The third time it would point to Joe. So let's say you're printing these things out. So it would print Tom, Nancy, Joe. The fourth time through, nit would point here, and if names.end returned the last element in the list, well, now nit1 would be equal to this last element, and we'd fall out of the loop prematurely, and we'd never print Mary. That's why it's so important that the end method actually return a pointer to the sentinel node rather than the last element in the list. Okay? Questions there? Finally, the last one, which most of you did quite well on with one exception. So here you were given a vector that you were pushing back new persons. So you pushed back 4 of them. So you ended up with 4 pointers to Mickey, Bugs, Daffy, and Winnie. And then you were setting the best friend pointers. So this piece of code was making the first 3 entries point to the next person. So Mickey pointed to Bugs, Bugs pointed to Daffy, Daffy pointed to Winnie, and the last one made Winnie point back to Daffy. Now, the only big issue I saw here was some confusion, because I think a lot of you saw equal friends, well, I'll do it with Winnie, where you see equal friends 2. And so a lot of people would say that Winnie's best friend pointer pointed to there. That's not right. It does not point to friends of 2. Okay? It points to the memory, it points to, let's say that this right here is 0x2000. Let's say this is 0x3000. Say this is 0x4000. Unfortunately, darn it, I can make it smaller. There we go. Move it down. And Winnie is 0x5000. So what actually happens, friends 0 is 0x2000. Friends 1 is 0x3000. Friends 2 is 0x4000. And friends 3 is 0x5000. So when you say that friends 3 best friend equal friends 2, what you're actually saying here is that this BF is equal to 0x4000, which is the value of friends 2. Okay? And since this is now 0x4000. That means we're actually pointing to that piece of memory right there. Okay, so again, this is 0x2000, 0x3000, 0x4000, 0x5000. Value here is 0x2000, 0x3000, 0x4000, 0x5000, and this is 0x4000 after the assignment. Therefore, it's actually pointing directly to here. Okay. Friends might be, for example, at location 0x1000. So this entry 2 is presumably something like 0x1008. And that is not what your BF pointer is pointing to. Okay, so is that point clear? That's the only major issue I saw with the diagrams that I looked at. Okay? So, any other questions, you can come up afterwards and ask me about them. The final exam I anticipate being the same format with the last lab in April. So the last lab of the semester, again, you'll have the entire lab period to do some coding problems. Then the final will be a written exam, probably only an hour 15 minutes, because it's only going to cover, it's not going to be a cumulative exam, it's going to cover the material since the last exam. And it's also going to include, I know there was something, linked data structures, because we started linked data structures the Tuesday before break, so you'll be expected to know that as well. Okay, so if you look at what we have left in the semester, we have recursion, which we are starting today, and trees, and then we'll revisit big O notation at the end of the course. Okay? So pointers, I think, is probably the hardest topic to get your minds around in this course. Recursion, nipping right at its toes at number 2. If this was a horse race, recursion would be also a very difficult concept for many of you to get at. So just a second, I don't think my notebook software is up right now for some reason. Let me just get that up. You can take a moment. Okay, so you've probably seen recursion before without really being aware of having seen it. So one of the classic recursion is when a problem or solution is expressed by solving one or more similar smaller problems and combining the solutions. So probably the classic example is factorial. you may have seen that n factorial, the definition of it is 0 factorial is 1, 1 factorial is 1, and n factorial equals n times n minus 1 factorial. So this is a recursive definition because we're expressing it by solving a similar smaller problem, which is n minus 1 factorial. Once we have the solution to n minus 1 factorial, we combine the solution by multiplying it by n. So in this case, there was only one smaller problem, and we multiplied that solution by n to get n factorial. And we had what we call the base case, which is what ends the recursion, and this is the recursive case. Okay, so the recursive case is the one that expresses the problem in terms of smaller problems and does some combination. The base case, at some point you have to stop the recursion and actually give a solution. If I didn't have 0 factorial equal 1 and 1 factorial equal 1, I could get into what's called an infinite recursion, because if I had 3 factorial, I would say that would be 3 times 2 factorial, which is equal to 3 times 2 times 1 factorial. And if I didn't stop it, now it would be 3 times 2 times 1 times 0 factorial. But if I didn't stop it, I would keep going. 2 times 1 times 0 times minus 1 times, minus 1 factorial. Hopefully you get the idea that I'm headed quickly down to negative infinity, which is never stopping. So the base case is what stops the recursion. So recursion always has two essential elements: a base case, one or more base cases to stop the recursion, and then a recursive case. Okay, another classic case of recursion is the Fibonacci numbers. Okay, these have all kinds of so-called wonderful properties, but again, the basic idea is that the 0th Fibonacci, there's some debate, so please don't get into it with me as to whether they start at 0 or 1, okay? I'm going to start them at 0 with the second one at 1. I understand that some other sources say that the first one starts at 1. Whatever. Okay, so these are the base cases. I saw some smiles, so apparently some of you are also familiar with that little debate. And then f of n equals f of n minus 1 plus f of n minus 2. So this is a case where we break it into two smaller problems and combine the solutions by adding them. So you can see that f of 2 is equal to what? Don't give me the final solution. What plus what? F of 1 plus f of 0, which is equal to 1 plus 0 equals 1. F of 3 equals f of 2 plus f of 1. We now compute it, f of 2. It is 1 plus 1 equals 2, and so on. So that's another classic recursive definition. So those are two mathematical functions that we say are recursive. You have seen, actually in CS 102, a recursive algorithm that we kind of defined recursively but implement it using a loop, and that is binary search. if you remember binary search takes a vector okay, so we have some values that are sorted. And let's say we're looking for the value 30. What's the first thing we do? What is the first element we look at based on what you remember from 102? 4. So we start with low equals 0, high equals 8, and we divide low plus high, divide it by 2, and we get 4. We compare 30 with 4, so what we say is if 30 is equal, we'll call this vector v, if 30 equals, so if, yeah, we'll just say if 30 equals v of 4, okay, success. Okay, we're done. What happens if 30 is less than v of 4? What do we do? Conceptually, what are we going to do now?
The low is 0 and we assign the high to 4. And then
Actually, we assign high.
and you read us to.
Right, so we actually are going to throw out the high end, the upper half of the array, and we're going to look at the lower half of the array. The way we do that is we set actually high to be equal to mid minus 1. Okay, but what we're doing is we're now we repeat the search lower half. So we're solving the same problem, but just searching the lower half. And if 30 is greater than v of 4, then we set low to be mid plus 1, but what we're really doing is searching the upper half. Okay, so there's kind of this idea of recursion in that we search the entire array by looking at the middle. If we find it's in the lower half, we throw out the upper half, and in effect, we recursively check the lower half. Okay, so there's got to be some base cases that stop this, right? This is one of the base cases, is success. Okay. Do you remember what the other so-called base case is? What's the other possibility that's going to stop this algorithm? Yes. It's not there. So we also, and do you remember what it was? I don't really remember you to remember what. Does anyone remember what condition stopped?
When the low is bigger than.
Correct. If the low became bigger than the high, then we knew the element, the other base case, is when low became greater than high, and we knew the element is not in vector. Okay, so here it's a little messier to write out the recursive description. But what I'm going to do is show you how you could write this. I'm going to show you your first recursive program. Okay? Recursion means that a function calls itself. Up to now, you've never had a function call itself. Actually, some of you cleverly tried it in CS 102. We see some of you calling main, okay, which we don't really like you to do, ever, but we certainly see it. Okay, so let's say I was going to write a recursive binary search, and I'm going to have it return the index of the element if it exists and -1 otherwise. So I'm going to call it bin search. And it's going to take a target, and it's going to take a vector of int. Remember, you have to, boy, if I could do reference, it has to take a reference parameter. Okay, so I'm going to define low, high, and mid. And going to start by setting low to be 0. I'm going to run out of room, so I wouldn't expect you to do this. I'd expect you to put these initializations on different lines, but I'm going to run out of room, so I'm going to put them all on the same line. V dot size -1, because high needs to point to the end, to the last element in the vector. And now I'm going to say mid. Actually, I can't say this. I'm sorry. How do I want to do this? I'm setting it up wrong. Actually, I'm not. I kind of set it up wrong. How do I want to do this? I'm going to call bin search helper. So I'm going to return bin search helper. I'm actually going to pass it target V, or run out of space, low is 0, and V dot size -1. I'll explain in a moment why I'm doing it this way. So all I'm doing is calling a function. Basically, I want to hide implementation details from the user. When I call bin search, they should only have to pass a target and the vector v. They shouldn't have to know how I'm implementing it. So what I'm going to do now is have bin search helper takes a target, a vector of ints v, int low, and int high. And what it's going to do is compute mid. So we're going to compute mid as low plus high divided by 2. And we're going to do a number of checks. So we're going to first check if low is greater than high, means we failed, so we're going to return -1. So that's our first base case, is if low is greater than high, we return -1. And I know I don't technically have to do this division in this case. So if you really want it, you could defer that operation until after you check to make sure that we're not past the end of the, that we haven't found something. The next check is to see whether V of mid equals target. If it is, what do we return? Not target. I know I return mid. I want to know its location. Okay, so I'm returning its location. Okay. If v of, well, we'll say if target is less than v of mid, then we will call bin search helper with our target v, low is still 0, and high -1, because what we're doing is searching the lower half. And otherwise, we're going to call bin search helper with our target v. Low becomes mid +1, and high because we're searching the upper half. So that is a recursive function. Bin search helper is a recursive function because it calls itself. Okay, and just like, so each time when it calls itself conceptually on, it's reduced the search space by half. It's still passing a pointer to the entire vector, but conceptually it has halved the search space. So it is looking at a problem that is only half as large. Okay, Alan?
I think you have a mistake in your first bin search helper.
It's like mid -1.
Ah, you're right. Thank you. It is mid -1. Thank you.
Well, and it should start at low, right, not 0.
Yes, thank you. Double whammy. Low. So low, comma. Yes, thank you. Low, comma, mid -1. So we're going from the lower half. Thank you. So that's what that is. Okay, so each time we've halved the search space. Now, I would accept an argument that says it was so much nicer looking when it was a loop. That's a fine argument to make, okay? However, I needed to show you a recursive algorithm that you've already seen, and quite frankly, I think Towers of Hanoi, while it's a classic recursion problem, is a fairly hard one to get your mind around as a first recursion problem. So bin search or binary search is something that you had already seen. And again, the reason I had a helper function is that I work in graphical user interfaces, human-computer interaction. And one of the fundamental tenets of human-computer interaction is you don't expose gory details to users. So in this case, when they call bin search, all they care about is they have a target element and a vector, and they want to know the location of the target element in the vector. They don't need to know how you implemented the silly algorithm. So that is why there's a one line in bin search, and all it does is it calls a helper function. That helper function is what contains the gory details with low and high. Okay? Now, the big question is, how does this magic work? Because when you call yourself recursively, one thing you might reasonably ask is, why don't my local variables get clobbered? Okay? So when I call bin search helper, you might think, well, wait a minute, all my local variables like mid might get clobbered, and if I need it in the future, when I return, it might have been changed. Okay? So that's the issue. Okay? Here I can maybe show it even more clearly if I write factorial. and write int n. So if n equals 0 or n equals 1, return 1, else return n times fact n minus 1. Okay? So let's say you go about trying to trace it, because you say Dr. van der Zanden always says trace functions if you're not sure what's going on. So I call it with fact of 3, and you happily write down n equals 3, because that's what n is equal. You see that n is not equal to 0 or 1, so it calls n times fact of n minus 1. So we're calling n times factorial of 2. So factorial of 2 gets called, and it seems like n gets set equal to 2. Kind of, right? Because now n is equal to 2 here. So it will call fact 2, will call n times fact of 1. Again, it seems like n gets reset to 1. Well, fact of 1 is going to return 1, right? Because n is equal to 1, so it returns 1. We come back here, oops, n is now 1. So 1 times 1 is 1. It returns 1 to fact of 3, but oops, 1, n is now 1. No matter what happens, I always return 1. That at least is a legitimate concern, right? That n is somehow getting stepped on. We don't want that. We want each invocation to remember its original value of n. So for fact 3, n should be equal to 3. For fact 2, n should be equal to 2. And for fact 1, n should be equal to 1. So we kind of want 3 copies of the function. And that is what happens in the computer. For those of you who have taken 160, you've seen the notion of stack frames. Okay, and I introduced them earlier in the semester as well. So what happens when you call a function is there is something called a stack that keeps track of the local variables. So when we start, main is the only function on the stack, and it has whatever local variables. When we call fact 3, it gets its own stack frame, and it sets n to 3. When we call fact of 2, it gets its own stack frame pushed onto the stack, and n is 2. And when we call fact of 1, we have n is equal to 1. So there's 3 copies of the function. There's not 3 copies of the code. There's only 1 copy of the code, but each call has a stack frame. We call this a stack frame. It contains copies, among other things. It contains local variables and parameters for that invocation of the function. Okay, so when fact 1 returns, it gets popped off, and it returns 1 to fact 2. So now fact 2 has n as 2. It multiplies the result when it has when it says n times fact of n minus 1. It's going to multiply 2 times the return value, which is 1, and it will return 2 to fact 3. And it will pop itself off. Then fact 3 is now executing n times fact of n minus 1. Well, this returned 2. That's what this is. N is 3. 3 times 2 is 6. It returns 6 to main, and it pops itself off the stack. So that's what's happening with recursive functions. In fact, with any function, that is what is happening. When you call a function, any function, it is allocated a stack frame at the top of the so-called stack. It is given room for its local variables and its parameters. It executes. When it's done, it pops itself off of this stack, and it returns its value to the calling function. So any questions about that? Okay, well, yes. So, you don't have to have some kind of running what?
You usually have like a running product variable.
No, you don't have to have a running product variable here.
It's just like n stuff.
Pardon?
N stuff.
N what?
The variable n stores the running product.
No, n is not storing. So n is not storing it. N is only storing the local value. The return value is kind of what's storing the product. The return value is what's keeping this running product for you. Okay? So we'll pick this up on Tuesday. We'll go over the Towers of Hanoi problem in Dr. Planck's notes, and then we'll go into the Sudoku solver in his notes.